We all know that ancient civilizations were technologically limited, working with stone tools, basic metallurgy, and manual labor to build their monuments and create their artifacts. But what if I told you that scattered across museums and archaeological sites around the world are tools, actual physical tools, that display precision engineering on par with modern machine work, created thousands of years before lathes, drills, and precision measuring instruments were invented? Doesn't make sense, does it? Stone cylinders bored with such perfect symmetry they could be mistaken for factory-made parts. Metal objects forged at temperatures that shouldn't have been achievable. Cutting implements so sharp and precise they rival surgical scalpels. Yet these tools exist, tested, measured, and authenticated as genuinely ancient. Today, we're examining 4 of the most impossible ancient tools ever discovered. Objects that look like they were manufactured yesterday, but are actually thousands of years old. And the uncomfortable questions they raise about what our ancestors really knew. Let's start with something that should be simple but isn't. A stone drill core from ancient Egypt. In the early 1980s, engineer and researcher Christopher Dunn was examining artifacts at the Cairo Museum when he came across a collection of cylindrical granite cores, remnants from ancient stone drilling operations. These cores are what's left when you bore a hole through solid rock, the central column of material that's removed in the process. They're common in archaeological sites throughout Egypt, evidence of the stoneworking techniques used to create everything from small vessels to massive sarcophagi. But when Dunn examined these cores under magnification and measured them with precision instruments, he discovered something that shouldn't be possible. The cores showed clear spiral grooves, the marks left by the drill bit as it cut through the granite. But the pitch of these grooves, the distance the drill advanced with each rotation, was impossibly fast. Modern diamond-tipped drills cutting through granite typically advance at a rate of about 1 millimeter per revolution under ideal conditions. The ancient Egyptian cores showed advancement rates of up to 2 millimeters per revolution, twice as fast as modern equipment. Even more baffling, the cores showed no signs of the kind of damage you'd expect from such aggressive cutting. No chipping, no cracking, just smooth, even spiral grooves as if the granite had been cut like soft cheese. Dunn calculated that achieving this cutting rate would require enormous downward pressure, possibly as much as 2 tons, combined with rotational speeds of at least 500 revolutions per minute. But ancient Egyptian stoneworkers supposedly used copper tools and abrasive sand, a technique that involves rubbing or grinding away the stone gradually. There's no evidence they possessed the kind of machinery needed to generate such pressure and speed. When modern stoneworkers have tried to replicate these cores using Bronze Age technology, copper drills and sand abrasives, they achieve advancement rates measured in fractions of a millimeter per hour, hundreds of times slower than what the ancient cores demonstrate. Some researchers suggest the Egyptians might have used some kind of unknown drilling compound, a paste or liquid that somehow made the granite softer or easier to cut. But no chemical analysis of the cores has revealed any residue that would support this theory. Others propose that the ancient Egyptians possessed drilling equipment far more advanced than we give them credit for, possibly powered by mechanisms we haven't discovered yet. But again, no archaeological evidence of such machinery has ever been found. The granite cores remain one of Egypt's most persistent technological mysteries, physical proof that ancient stoneworkers achieved results we can't replicate with known ancient techniques. Dr. Denny Stocks, an experimental archaeologist who has spent decades studying ancient Egyptian tool technology, attempted to drill granite using reconstructed Bronze Age tools. His results, published in multiple academic papers, showed that while it's possible to bore holes in granite using copper and sand, the process is agonizingly slow and produces marks distinctly different from those found on the ancient cores. He concluded that, while we can prove the Egyptians could drill stone, we still cannot explain how they achieved the precision and speed evident in the surviving artifacts. The cores sit in museums, cataloged and measured, yet they continue to defy our understanding of what should have been possible 4,000 years ago. But Egypt's stone-working mysteries are just the beginning. In the ancient city of Pumapunku in Bolivia, there are stone blocks so precisely cut they challenge not just our understanding of ancient technology, but of physics itself. Pumapunku is part of the larger Tiwanaku site, a pre-Columbian civilization that flourished in the Andes between roughly 5 and 1000 CEA. The site is famous for its massive stone structures, but Pumapunku in particular is known for something unique: the precision of its stonework. The blocks at Pumapunku are not just large, they're immaculately crafted. Some weigh more than 130 tons, yet they feature surfaces so flat and smooth that modern engineers have measured them and found deviations from perfect flatness of less than 1 millimeter across spans of several meters. These surfaces would be difficult to achieve even with modern machine tools. Even more remarkable, many blocks feature intricate interlocking joints, grooves, and channels cut with such precision that adjacent blocks fit together with gaps measured in fractions of a millimeter, too tight to insert a sheet of paper. The blocks are made from andesite and diorite, volcanic stones with hardness ratings of 6 to 7 on the MOS scale, harder than most metals available to ancient peoples. Yet the surfaces show evidence of having been cut, shaped, and polished with extreme precision. How? The Tiwanaku people are not known to have possessed metal tools hard enough to work these stones effectively, and there's no evidence of advanced mechanical equipment at the site. Engineer Brian Forster, who has extensively documented Pumapunku, notes that some blocks feature small, perfectly square holes drilled with such precision they appear to have been made with modern drill bits. These holes are often interconnected with channels inside the stone, creating complex internal geometries that would require not just drilling but the ability to see inside the stone or to work with perfect three-dimensional planning. Archaeologist Alexei Vranich, who has studied Tiwanaku for decades, acknowledges the extraordinary precision, but argues that it could have been achieved through patient, skilled work with simple tools like stone hammers and copper chisels, combined with abrasives. However, experimental archaeology has struggled to replicate the precision of Pumapunku's stonework using these methods. Modern stoneworkers who have attempted to recreate similar blocks using Bronze Age techniques can produce flat surfaces, but not with the same degree of accuracy, and certainly not with the same speed that would have been necessary to complete a structure of Pumapunku's scale. The site contains hundreds of these precision blocks, some weighing dozens of tons. If each block took months or years to craft using simple tools, the construction of Pumapunku would have required centuries of continuous work by a massive workforce. Yet archaeological evidence suggests the site was built in a relatively short time span. So we're left with a paradox: precision that requires advanced tools, but no evidence of those tools. Massive blocks that seem to have been shaped with ease, yet no known technology to accomplish it. Some researchers have suggested the Tiwanaku possessed knowledge of stone softening compounds, possibly plant-based acids that could temporarily make hard stone easier to work. Local legends do speak of such substances, but no chemical analysis has confirmed their existence. Others point to the possibility of lost advanced tools, possibly made from materials that decomposed over time. But this requires us to imagine a sophisticated toolkit that left no archaeological trace, a difficult hypothesis to defend. What we're left with are the stones themselves, tangible, measurable, undeniably ancient, and impossibly precise. They sit in the Bolivian highlands, weathered by centuries but still displaying craftsmanship that modern engineers respect and struggle to explain. But precision stonework, as remarkable as it is only one category of impossible ancient technology. Let's turn to metallurgy, specifically to an object so advanced it shouldn't exist at all: the Iron Pillar of Delhi. Standing in a courtyard in Delhi, India, is a pillar of iron roughly 23 feet tall and weighing approximately 6 tons. It was erected sometime around 400 CE during the reign of Chandragupta II, making it more than 1600 years old. That alone would make it historically significant. But what makes the Delhi pillar truly extraordinary is its composition. The pillar is made of iron with a purity level of about 98, remarkably high for ancient metallurgy. But even more astonishing, despite standing outdoors exposed to monsoon rains, heat, and humidity for over 16 centuries, the pillar has barely rusted. Its surface shows only a thin layer of oxidation, while modern iron structures in similar conditions would have corroded significantly within decades. Metallurgical analysis has revealed that the pillar's resistance to corrosion is due to an unusual protective coating, a layer of crystalline iron hydrogen phosphate formed by the interaction of iron, phosphorus in the metal, and atmospheric moisture. This coating protects the underlying iron from further oxidation. But here's the mystery. Creating this effect would require an understanding of materials science and metallurgical chemistry that, according to conventional history, didn't exist in the 5th century. The phosphorus content in the iron is unusually high, about 1, much higher than typical ancient iron. This phosphorus, combined with the way the pillar was forged, creates the protective layer. But achieving this would require precise control over the smelting process, maintaining specific temperatures and atmospheric conditions in the furnace, something that's difficult even with modern technology. How did ancient Indian smiths achieve this? Some researchers suggest it was accidental, that the particular ore used naturally contained high phosphorus, and that the forging process happened to create the right conditions. But this explanation seems insufficient, given the sheer size of the pillar. Forging a 6-ton column of iron in one piece would require welding together multiple smaller pieces using a technique called forge welding, heating the iron until it's nearly molten and then hammering it together. Doing this while maintaining uniform phosphorus content and avoiding contamination would require extraordinary skill and consistency. Modern metallurgists who have analyzed the pillar express admiration for the craftsmanship. Dr. R. Balasubramaniam, a materials scientist who has published extensively on the Delhi pillar, concluded that the ancient Indian ironworkers possessed empirical knowledge of metallurgy that was, in some respects, more advanced than what medieval European smiths would achieve 1,000 years later. The pillar stands as a monument not just to a ruler, but to a level of technical expertise we're still trying to fully understand. But if the Delhi pillar represents mastery of large-scale metallurgy, our final tool takes us in the opposite direction, to the world of microengineering. In the rock shelters of Bhimbetka, in central India, archaeologists have discovered microlithic tools. Tiny stone implements so small and precisely crafted, they challenge our understanding of ancient motor skills and tool making. Microliths are small stone blades or points, typically less than an inch long, often as small as a few millimeters. They were created by carefully striking flakes from larger stones and then shaping those flakes through pressure flaking, using bone or antler tools to remove tiny chips along the edges. The result is a tool so small and delicate it seems almost impossible to have been made by hand. The microliths from Bhimbetka date back at least 10,000 years, placing them in the Mesolithic period. But their precision is what's truly remarkable. Under magnification, the edges of these tools show serrations and cutting surfaces so fine and regular, they resemble modern surgical blades. Each notch, each flake removed, is placed with apparent intentionality, creating complex geometries on a scale of less than a millimeter. Creating such tools requires not just skill, but extraordinary fine motor control and visual acuity. Modern flint knappers, artisans who specialize in recreating ancient stone tools, can make microliths, but they often struggle to match the precision of the ancient examples. Even a slight mistake, too much pressure, a flake removed at the wrong angle, can ruin the piece. The fact that ancient peoples produced these tools in quantity, archaeologists have found thousands of them, suggests they had not just individual talent, but a widespread technological tradition capable of teaching and maintaining such skills. But what were microliths used for? Their small size makes them unsuitable as standalone tools. Instead, they were likely hafted, set into wooden or bone handles to create composite tools like arrows, knives, or saws. This required another level of sophistication, crafting handles with precise slots or grooves to hold the tiny blades, then securing them with adhesives made from tree resins or animal glues. The end result was a tool that combined multiple components, each crafted with precision, into a functional implement. What makes this even more impressive is that it represents a form of mass production. Microliths weren't unique ceremonial objects. They were everyday tools created in large numbers for practical use. This means ancient peoples had developed standardized techniques, teaching methods, and quality control sufficient to produce hundreds or thousands of nearly identical precision tools. It's a level of technological organization we don't usually associate with the Stone Age. Dr. Sheila Mishra, an archaeologist who has studied India's microlithic traditions, describes them as evidence of a revolution in human cognition and dexterity. She argues that creating microliths required not just physical skill, but abstract thinking, the ability to visualize the final tool before beginning work, to plan each strike and flake removal in advance, essentially to think in 3 dimensions, and at microscopic scales. Attempts to replicate these tools using only Stone Age technology have shown that it's possible, but incredibly difficult. Modern artisans working under controlled conditions, with magnifying glasses and plenty of time, can produce microliths of similar quality. But the ancient toolmakers did this routinely, possibly by firelight or in dim rock shelters, with no modern aids, just their hands, simple tools, and extraordinary skill. Today, microliths are displayed in museums, often overlooked by visitors who are drawn to larger, more impressive artifacts. But to those who understand the technical challenges involved, these tiny stone blades represent something profound, proof that 10,000 years ago, humans possessed manual dexterity and precision engineering capabilities on par with the finest craftsmen of any era. 4 tools, 4 impossibilities. Granite cores drilled faster than modern equipment can achieve, stone blocks cut with precision measured in fractions of millimeters, an iron pillar that defies corrosion through metallurgical knowledge that seems ahead of its time, and microliths so small and perfect they challenge our assumptions about ancient capabilities. Each of these tools forces us to confront an uncomfortable question: how much of ancient technology have we underestimated? We tend to think of technological progress as linear, each generation building on the last, advancing steadily from simple to complex. But these artifacts suggest something different, that ancient peoples achieved levels of precision and sophistication in specific areas that we've only recently matched or, in some cases, still struggle to explain. They remind us that intelligence, creativity, and skill are not products of modernity, but timeless human traits. The hands that drilled those granite cores, that shaped those stone blocks, that forged that iron pillar, and that crafted those microliths were no less capable than ours. They simply applied their capabilities in ways we've forgotten, using techniques we've lost, achieving results we still admire. And perhaps that's the real lesson of these impossible tools, that the past holds more knowledge than we give it credit for, and that the line between primitive and advanced is far blurrier than we like to think. If you want to see more ancient technologies that challenge modern science, subscribe and let us know in the comments which ancient tool or artifact you want us to investigate next. Because the deeper we dig into history, the more we realize the ancients were capable of far more than we ever imagined.